Hey physicists, we're going to look at the collision we did previously with the same initial conditions, a 3 kilogram ball moving at 8 meters per second, a 2 kilogram ball moving at 5 meters per second in the directions indicated. But the difference here is that this is going to end up being an elastic collision. That's going to be where the two balls end up bouncing off each other. And in the narrow definition, not only do they bounce off each other, but there's no loss of kinetic energy. We're not going to worry too much about that. We're going to look at conservation of momentum right now. Okay, so we have the initial conditions and angles here. We also have a final condition just put in a component form for object 1, that after the collision it ends up heading off at a direction of the direction, but the components 6.67 meters per second in the x direction, 2.13 meters per second in the y direction. So it kind of ends up, after the collision, it kind of goes off in kind of a direction like that. All right. We have a pretty good idea what's going to happen with our 2 kilogram ball. Like before, our center of mass is going to continue moving along in a straight line because there are no external forces, so that'll keep on moving. So this is going to end up kind of heading probably somewhere that direction. I'm going to add in this data that we have here into the table. This portion of the table is the same as we had before, and we have the same conditions as before. Our initial momentum in the x direction can equal our final momentum in the x direction. Our initial momentum in the y direction is going to equal our final momentum in the y direction. We'll go ahead and fill this out. So our final velocity in the x direction, 6.67, and 2.13 in the y direction. All right. Okay, I'm just going to figure out what my momentum from object 1 is. I'm just going to do a little bit of multiplying. I'm just going to pause this for a few moments, but you probably have an idea that momentum is going to equal to mass times velocity. My mass is here, my velocity is here. All right, so by multiplying, I figured out my momentum in the x direction and y direction from ball 1. My total momentum, of course, here and here stay the same from before and after the collision in each of the two directions. To figure out the contribution from mass 2, we can just subtract that. Total momentum, 27.87. We'll subtract our 20.03, and we get 7.84 kilogram meters per second of momentum in the x direction from ball 2, and then we'll take what does this end up being? 6.40 minus what's going to equal negative 4.92. Do quick little work on the calculator. Minus 11.32. Okay. Hey, so now we can go back and just rearrange this equation. A velocity is going to be equal to momentum divided by mass. We'll do that for each of these two. I'll do that calculation. Put it in here. Hey, so dividing momentum by our mass, I end up getting velocity in the x direction. Just make sure. Oops, yeah, by 2. I get velocity in the x direction, 3.92 for the ball, 2 kilogram ball, and negative 5.66 in the y direction. Yep, so it's going to head off somewhere like that. Similar to last time, if you want to figure out what this velocity is, Pythagoras could end up telling us a squared plus b squared plus c squared. You can figure that out. And of course, then if we wanted to figure out this angle, we could figure out our angle from the inverse tangent of our values. What does this end up being? Negative 5.66 divided by 3.92, whatever that works out to be. All right. Hey, but that's how we take a look at conservation of momentum in an elastic collision.